Well, thank you, everybody. So our last talk for the morning session is going to be Martin Homann. Martin's talk involves understanding false positives in terms of terrestrial microbiology, and I will give it to Martin.
Thank you so much. Can you all hear me all right? Brilliant. Yeah, thanks for the introduction. I'm really happy to be here with you today. We already heard some really exciting talks, and in the following, I would like to talk about how Earth's earliest record of fossil traces of ancient microbial life can help us to avoid astrobiological false positives. There might be some overlap with previous talks, but that's just the nature of it. So let's quickly have a look what are biosignatures again. So biosignatures can be defined or are objects, substances, or patterns whose origin specifically requires a biological agent. And candidate biosignatures can be ranked by three main criteria: reliability, survivability, and of course, in a planetary context, also detectability. Usefulness of a certain biosignature also strongly depends on the improbability of non-biological processes forming these structures. And this brings me directly to false positives. What are false positives? So these are basically abiogenic processes that mimic biogenic processes and that can lead to the formation of lifelike structures. Quite famous examples, for example, was the Allen Hills meteorite, a Martian meteorite, where people in the 90s thought they have identified there are some filaments in there, and they thought they might be of biogenic origin, but later on it turned out that these might just be abiogenic nanobacteria-like structures. Also, some of the most ancient, direct fossil evidence for life, ancient microfossils from the apex chert. These you can see here. A lot of work has been done actually on these structures, and it turns out that these might also just be mineral artifacts, so sheets of phyllosilicates that are kind of coated by carbonaceous and organic matter. So really, we have to look. It's really a cautionary tale with a lot of these simple structures. The same thing is true for hematitic filaments that have been reported from 3.7 billion-year-old hydrothermal vent deposits from Greenland. Also there we see some kind of very basic filamentous microstructures, and similar structures can also be formed actually in abiotic mineralized chemical gardens. So these are processes that happen in pH-driven inorganic chemical reactions that can actually produce filaments that look quite similar. And we have already seen, already mentioned before, some of the most ancient potential signs for life, these ancient stromatolites. These are also quite controversial with an age of 3.7 billion years. You see this is a field image. They are coming from highly metamorphosed, so really overprinted rocks that have been deformed and cooked up. They don't have any internal laminations anymore. And as we have seen before, these structures might just form through structural deformation. So here you see one of these domes in cross-section, but in the side, everything is flat and stretched out. So once again, the take-home message here is that morphology or morphological evidence alone is insufficient to determine if a structure is biogenic in origin. So what lines of evidence provide the clearest validation of ancient biology in the rock record? Well, over the years, there have been a few very basic criteria have been established. For example, did the object really form in a former habitable environment? The environmental context of a certain sample is really important. Is it surely endogenic and syngenetic to the host rock? Are morphology and biofabric consistent with a biogenic origin, or is there any kind of mechanism that can form similar structures in an abiogenic way? And also, is the chemical and isotopic composition distinctly lifelike or not? So in the end, we have heard it in previous talk, we really need multiple independent lines of evidence to establish the biogenicity. So the more, the merrier, to prove if a structure was really biogenic in origin. If we talk about fossil biosignatures in deep time and space, of course, if you're looking for like life on other planets, we often look for life as we know it. And life as we know it is carbon-based. We need water as a solvent. We've got the famous Schnapps element that are incorporated in most macromolecules of life on Earth. When we are looking for ancient traces of the earliest life on Earth, of course, we're looking in former aquatic sedimentary deposits of the Archean. So lithified aquatic sediments, what are the main lithologies we are looking at? Silicified carbonates and cherts. Sandstones, however, have been quite overlooked in the previous literature or in previous studies because people often don't believe that you can also preserve certain biogenic structures in sandstones. But I will show you later that under the right conditions, also sandstones are a great place to search for ancient traces of life. What are we looking for? Of course, we are looking for morphological and chemical biosignatures, so traces of microbial life that potentially form microbial mats or biofilms and is preserved as organic matter. So something really important is also that we need some sort of early diagenetic mineralization to preserve these ancient traces of life. Otherwise, we will not be able, of course, to detect them. And that's also true if you're looking for astrobiological biosignatures. If there's no way to preserve your structure, you will not find them. So that's really key to keep in mind. We have already heard in the previous talks a lot, we talked about microbial mats. Maybe not all of you are familiar what they actually are. So these are laminated microbial communities that are mainly formed by bacteria and archaea. And it really depends on the environment at which these mats are thriving, what kind of structures you form in the end. So Frank has already talked about microbialites. These are biogeochemical sediments. Famous example are stromatolites and thrombolites. The oldest accepted stromatolites are 3.5 billion years in age, coming from the Pilbara Craton in Australia, but also in sandstone environments, so in former coastline environments, microbial mats are thriving, and under the right conditions, they can also be preserved in the rock record. And here's a little video I wanted to show you. These are we are here like in Tunisia at low tide. You can actually peel these microbial mats off with a knife. These are really carpet-like structures. They're very, how we say, dense, and it really gives you a feeling of how these structures maybe once have looked like on the early Earth. You just put them back, and they're happy and continue to grow. So there are, of course, different life detection techniques that we can use, and these range from microscopic observations to hand sample and outcrop observations up until planetary scale observations. And I'm quite similar to Frank. I'm a field geologist, a field geobiologist, so I go to like outcrops on the Archean rock outcrops, and I take hand samples, I look at them under the microscope, and I study the chemical composition of these rocks. So if we are now talking about a few examples for biosignatures in deep time, the question is, where can we find them? Deep time meaning like Archean, like older than 2.5 billion years. There are actually only a few places left on Earth where we can still find Archean rocks, Archean sedimentary rocks that have escaped major deformation and alteration events. And these two places is the Pilbara Craton in Australia, and the other one is the Carpval Craton, or it's the Barberton Greenstone Bed that is located in the Carpval Craton of Southern Africa. And I've worked a lot in the Carpval Craton or in the Barberton Greenstone Bed. And in the following, I would like to show you a few examples of early life from these rocks. So the Barberton Greenstone Bed is a beautiful place to work. It comprises rocks that have an age between 3.5 and 3.2 billion years in age. And it has also been a World Heritage Site since 2018. So it's really protected for future generations of geo and astrobiologists to study these beautiful rocks. There are a lot of different traces of early life preserved in the Barberton supergroup. I know there's a lot of information. It's basically I want to show you we've got the Unverwacht, a fig tree, and Moodys Group on top, and microfossils and microbial mats in the Unverwacht group. They typically only are preserved in carbonaceous cherts that you see here in these black lines indicated. The Moodys Group on top, these are siliciclastic rock units. So we've got sandstones and conglomerates, and there we've got fossil microbial mats. And in the following, I would like to just go upwards a bit in the stratigraphy and highlight a few of these earliest traces of life in the Barberton Greenstone Bed. So let's start with rocks from the Buckreef chert. The Buckreef chert is quite a massive accumulation of chert. It's a bit between 250 and 400 meter thick. It can be traced for more than 50 kilometers along strike. It contains quite a peculiar black and white banded chert, so it's almost pure silica, and in places we also see some silicified evaporites. So we are really in a nearshore coastal paleo environment, and especially Mike Tice and Don Lowe, they had a closer look at these carbonaceous laminations in these black cherts, and they interpret these structures as fossilized microbial mats that were once really draping these sand grains. They're really nicely preserved. We also in places see eroded and rolled up mat fragments that once again, like in modern analogs, they indicate former cohesive consistency of these biofilms and mats. And if you zoom in a bit more and you look at scanning electron microscopy, you also see preserved and silicified, deeply embedded biofilms. And the transmission electron microscopy also shows that they are still composed of carbon, which is also then again shown by Raman spectroscopy. So you've got mature carbon that has this typical D and G peaks. In that case, it's consistent with, 300 degrees Celsius, which is also the metamorphic degree of the surrounding host rock. So these structures are really indigenous, and they did not enter the rock at a later stage. A few more, perhaps a bit more controversial microstructures in the Buckreef chert are just simple filaments. As I've shown you before, these are not necessarily of biogenic origin. Other structures are spheroidal microstructures. Once again, this is a very simple micromorphology. These might just well be mineral grains that were coated and at a later stage. So it's really not conclusive just to have like an old rock and say, I see like some spheres, and then you conclude this must be life. You need more evidence. So these are kind of questionable microstructures. Some really interesting microfossils that have been found and discovered in the Buckreef chert of the Unverwacht group already in the 1960s are these lenticular microfossils. And people still don't know what they actually are. People speculate that these might be planktonic microorganisms. Why are they interesting? Because we not only find them in the Barberton Greenstone Bed, but we also find them in the Pilbara Greenstone Belts. So it's quite strong evidence that these might actually be of biogenic origin. People have measured the organic carbon isotope values that range between -30, -40 per mil, which is indicative for or supports a biogenic origin. And once again, if you look a bit closer under the scanning electron microscope, you see really organic walls nicely preserved. And with X-ray absorption spectroscopy, you can also see that there are potentially some peaks indicating some various molecular groups that are already or still preserved in these microfossils that are quite similar to microfossils of younger chert units, for example, the gunflint chert, and also modern microfossils. So all in all, this is kind of strong proof that these structures really were very likely biogenic in origin. So moving upward a bit in the stratigraphy, we are now at the Mendon chert. These are 3.3 billion-year-old cherts, and in the 80s there was some work or publication by Gary Byerly who said they have described these structures as potential stromatolites. So once again, these kind of like crinkly laminations, little domes. This is an outcrop view, so we are looking downwards on these cauliflower-like structures. So potential stromatolites, if you have a closer look and you cut your sample open, you see these kind of domal to pseudocolumnar growth morphologies that really resemble what we think stromatolites should look like. And I don't know if Frank is still here, but that's of course, once again, it's only morphology, so we don't want to confuse that with an abiogenic structure. If you have a look at the thin section, you see that these crinkly organic-rich laminations are often overgrown by idiomorphic tourmaline minerals. These tourmalines are magnesium, borium, and chromium rich, and it has been postulated that these tourmaline mineralization was likely driven by boron-rich hydrothermal fluids. So is really the question, are these stromatolites or are these maybe just abiogenic sinter deposits? It's still kind of an ongoing debate. Also, we've got some organic carbon isotope measurements. These show values that, once again, are consistent with a biogenic origin. The values range between -34 and -22 per mil. And that's a thin section image and a corresponding Raman intensity map. Also here we see in these red colors that we definitely have some preserved organic matter or mature organic matter we call kerogen. That has seen temperatures above 400 degrees Celsius. And so there's definitely organic matter preserved, but if we look at modern hydrothermal systems or hot spring deposits, for example, this is a beautiful place in El Tatio in Chile. It's about above 4,000 meter height, so it's really high, air is really thin. It's a great place for geobiologists and astrobiologists to work, because these are places where, of course, hot hydrothermal fluids enriched in silica erupt and form these geyserites. These are places where it's not always clear what is biogenic and what is abiogenic. So you have a lot of mineral precipitation, but then you also got really slimy microbial mats that just love to live there, and that they are fossilized in situ there. So here a few field images of microbial mats. Often these mats here are like some rafts that are just floating around. The tops are already starting to silicify just due to evaporation. And here you see another close-up of this silicification. Other really interesting structures are these little knobby structures that people call digitate structures. So these are interesting because a few years ago, Ruff and Farmer have basically described similar structures on the surface of Mars, and they speculate. So these are images of the Martian surface, and these are images from El Tatio in Chile, and they have similar spectral characteristics, and they kind of speculate that we could use potentially these digitate structures as biosignatures. And that's because, of course, in modern hydrothermal systems, you've got a lot of microbes, so microbes are just living there. But the question is, does the morphology really require the presence of microbes or not? So what is actually forming these structures? A few years ago, I was involved in a study led by Zhang Gong, where had a closer look at these digitate structures and how they form. And interestingly, even though we see like really nice laminations in these digitate structures, there's almost no organic matter preserved. There are no filaments, no microfossils preserved. And he back then concluded that these structures formed just to evaporitic rise of silica. So it's basically because you've got strong winds And these microstructures often grow perpendicular to the main wind direction, which you see here. So that's a field image, the wind coming from here, and most of these structures are really growing towards the wind. So it's really, the idea is really that potentially the wind and the evaporation leads to capillary rise, and that's why you form these layers. And enriched in these layers are just detrital sedimentary particles. I'm not saying that, all these structures are formed just abiogenetically, but it's not so simple that we can say like, hey, we've got digitids on Mars, so there must have been life. So just a cautionary tale, similar to Frank's comment earlier. So in the remaining time of my talk, I would like to talk about the more microbial mats. I really love them. So these are more microbial mats from the Moodys Group. That is the uppermost unit of the Barberton Greenstone Bed. So these rocks are 3.22 billion years in age, and that's a nice big polished slab. So you basically it's a coarse-grained sandstones, and all these dark, wrinkly laminations we interpret as fossilized remnants of microbial mats. So let's have a closer look at the Moodys Group itself. It's actually the oldest well-preserved continental to marine transition that we have preserved on Earth. It's a very high-resolution archive. It was probably deposited between 1 to 14 million years. Paleoenvironments range from alluvial to deltaic settings, so we are basically in a nearshore coastal paleoenvironment, and in this simplified stratigraphic column, you already see indicated in green where we find these mats really in nearshore environments. They are really not preserved or not present in subtidal, so in deeper water environments. One field images. One field picture. You see, so these are all former sedimentary packages. They are overturned, so this is older here and this is young. So you can really imagine how you walk downhill and you take a lot of observations and you measure stratigraphic profiles, because that's what you do in the field, because you want to kind of characterize the paleo environment. And preserved in these rocks, already visible in the field, are these fossil microbial mats interbedded with medium to gross-grained sandstone. And these structures really form a primary microrelief. So why do we think that? This is, for example, a sand ripple in cross-section. So the sedimentary structures are really well preserved. They're not deformed, unlike to these highly alterated stromatolites from Greenland. Nothing is really deformed here. So sedimentary structures are well preserved. That's why we have no reason to believe that these fossil mats are the result of any sort of structural deformation or secondary process. As I've mentioned before, we've got beautiful sedimentary structures. These just help us to characterize the environment of deposition and to constrain in what nearshore environments these former mats were thriving. And once again, this is too much information on this graph. I do apologize, but it just shows you all the stratigraphic columns that I've done over the years, and it just shows highlighted in green the places where we have fossil remains of microbial mats preserved. It's basically in an area that we can trace for 15 kilometers along strike, and they occur within a stratigraphic package of 1 kilometer. So it's really a huge area where these microbes were once living or where they are still preserved. Outcrop observations also show that the morphology of these mats really depends in which environment they were once living. So in more protective paleo environments, we form more complex, tufted microbial mats, whereas in environments where current speeds were too high or high enough to transport pebbles and conglomerates, mats tend to be flat. And this is again another indicator for the biogenicity of these structures, because you would expect that microbes or microbial mats adapt to the environment in which they were living. And they must have been, of course, sticky enough to not be eroded. So once again, a proof of their biogenicity. Other structures that we can see that are preserved there are microbial-induced sedimentary structures. So these are, for example, shrinkage cracks. These form when a microbial mat is drying out and starts to shrink and crack. If that's early silicified, they are really well preserved. We also see eroded mat fragments. in the outcrop. Sometimes they form also little conglomerates. And that's a polished slab image where you see mats in place and eroded mats, once again proving the syngenetic origin of these structures. And finally, we also got fluid escape structures. They are quite common in microbial mats because these mats, they contain mostly of water. Over 90% they are water-based. If you put a lot of sediment on top of these mats, eventually it will just start to migrate upwards and deform these mats at an early diagenetic stage. Of course, microbial-induced sedimentary structures have a bit of a bad connotation because a few years ago there was a paper by Nora Nofke, and she proposed that she has seen some microbial-induced sedimentary structures also on the surface of Mars. But once again, this is just superficial, so morphological features. There's no context, and in my point of view, that might be a bit geofantasy. It's just there's not enough proof to say like, oh, this looks like a mat on Earth. That's why we had life on Mars. But I really like microbial mats, and microbial sedimentary structures can really tell us a lot if it's done in the right way. But this is another cautionary tale. Morphology alone is not enough. A few thin section images of these mats of the Moodys Group. That's an entire thin section image. Here you see like a close-up. You really see that these mats are really preserved as organic-rich lamination that kind of drape and stabilize former quartz grains. And below is just a modern analog. This is a microbial mat dominated by Mycocoleus, so a cyanobacteria that shows kind of, you actually can see tiny little filaments that are draping and stabilizing sand grains. So probably very similar structures we see here, even though it's controversial. It's not really clear that these are cyanobacteria or not, but we can say they must have been probably filamentous in shape. A few more images. Here again, this beautiful preservation of these mats, and this is closely linked to early silicification. Without early silicification of these deposits, we would have not preserved them in such great detail. And these structures, they might or might not be interpreted as filaments, but the bottom line is really well preservation. And if we look a bit closer using scanning electron microscopy, we also see in the same samples where we see sufficient microbial mats, we see preserved and deeply embedded microbial biofilms. We see extracellular polymeric substances, so the matrices in which microbes are thriving, and that protects them. And we see also in situ preserved filaments or filamentous molds. These observations alone would not be, proof enough, but the context and the ensemble of observation really makes these structures believable as biosignatures. 10 minutes, perfect, thank you. So we also performed some Raman spectroscopy of these carbonaceous laminations. So these are thin section images and corresponding Raman intensity maps and the corresponding elemental peaks. We see clearly in red the presence of kerogen that is some sort of mature carbon, and really kerogen or organic carbon changes with increasing metamorphic degrees. So you have these D and G peaks, and if you increase the temperature, these peaks will change until you end up in a graphite. So this is the Moodys Group, this is green schist features. So these rocks have seen 340 to 360 degree, which is also the peak temperature the organic carbon has seen. So it's really a proof that they are syngenetic and have not entered the rock at a later stage. Okay. Another thing I've not really mentioned before is that we find these mats in the Moodys Group in two distinct paleoenvironments. One is like a coastal nearshore marine facies, and the other facies we interpret as fluvial in origin. And of course, depending on the environment in which these mats are thriving, in the fluvial settings, they are thicker because probably the current velocities were just stronger. And we can compare these mats visually, but we can also use organic carbon isotope analysis. and compare the fluvial with the organic matter preserved in the fluvial mats with the organic matter preserved in the marine mats, and they show distinct differences. For example, the fluvial mats show values between -24 to -18 per mil, which is consistent with the with autotrophic carbon fixation via the Calvin-Benson cycle, whereas the marine mats, they show more negative delta 13C org values down to -34 per mil, which might be best explained with the Wood-Lungdahl pathway that includes methanogens and sulfate reducers. Also, the nitrogen isotope analysis that we have performed show distinct differences between the fluvial and the marine mats. And this is another proof of the biogenetic origin of these features, because these are clearly values that are, how we say, consistent with a biogenic origin. So I know that might be a bit repetitive, but here's already my summary. A lot of things have already been mentioned before, but I think the key line is that we need multiple independent lines of evidence to actually prove the biogenicity of a certain structure. Early diagenetic mineralization is key for the preservation of any sort of biosignature, and silicified microbial mats or also biofilms are really robust evidence for early life on Earth. And if, in my point of view, if there was ever life on Mars, or still is, it might eventually, if there are microbes, they will eventually start to form a biofilm that eventually leads to the formation of a microbial mat. So these are really prime targets for astrobiological research. And yeah, with no further ado, I would like to thank you for your attention and happy to answer any questions.